we can define triple integrals in a very similar way to how we defined double integrals. So we're going to define a triple integral over a region T in 3 dimensions by a Riemann sum. So the integral over that region T of f of x, y, z dv is going to be a limit as, say, L, M, and N go to infinity of the sum from I equals 1 to L, the sum j equals 1 to m, and then the sum of k equals 1 to n. So it's a triple sum of f of x I j k, y sub I j k, z sub I j k, and then we're going to write delta v. So this is a Riemann sum, and it's a triple sum, so we can sum over the possible x, y's, and z's in our 3-dimensional domain, and each of those are getting multiplied by a little bit of volume. Now in Cartesian coordinates, our dv we're going to think of as being dx, dy, dz. So that our delta v we're thinking about as being a cube formed by delta x, delta y, and delta z. And the idea here is that if we let the number of these little cubes go to infinity, that's letting L, M, and N go to infinity, then the sizes of those cubes have to get smaller so that delta x, delta y, and delta z are all going to 0. And so that the triple sum that you see there becomes a definite integral. I now want to proceed with a couple examples of how you can evaluate a triple integral over a rectangular domain. So our first domain is going to be x's between -1 and 1, y's between 2 and 3, and then z's between 0 and 1. And so we're going to do an integral. That integral is going to be from, let's say, -1 to 1 in x, and then from 2 to 3 in y, and then from 0 to 1 in z. And we want to integrate x, y plus y, z. And we're going to do that dz, dy, dx. And so we're going to evaluate this as an iterated integral. But something I want you to notice is that the integrand here is really y times x plus z. So it's a function of y times a function of x and z. And so because of that, we can actually take the y integral out. We can write this as the integral from 2 to 3 of y dy, and then that's times the double integral from, say, -1 to 1 in x and 0 to 1 in z of x plus z dz dx. Okay, so we're going to move right along here. We're going to write this as, first we're going to do the y integral. So the antiderivative of y is 1/2 y squared. We want to evaluate that between 2 and 3. And then we're going to start doing the double integral. So that's an integral from -1 to 1. And then we want to look at the antiderivative of x plus z with respect to z. So that's going to become xz plus 1/2 z squared. And I want to evaluate that between 0 and 1. And I still need to integrate that dx. Well, this is going to become, let's see, 3 squared is 9, so we're going to get 9 halves minus, and then we're going to get 2 squared, which is 4 over 2. And then for the inner integral, or for the double integral that we're still evaluating there, we're going to integrate from minus 1 to 1. Now I'm going to evaluate at z equals 1. I'm going to get x plus a half. And when I evaluate at z equals 0, I'm going to get 0. So I'm going to integrate that dx. Okay, so 9 halves minus 4 halves, that's going to be 5 halves. And then I'm going to integrate from minus 1 to 1, x plus a half. And that's going to give me a 1 half x squared plus 1 half x, evaluated between minus 1 and 1. And that's going to give me, let's say, 5 halves times, let's see, we're going to get 1 half plus, plugging in 1, we also get 1 half. Then we're going to get minus, and then plugging in negative 1, I'm going to get 1 half minus a half. So we're going to get 5 halves times 1, because, of course, these cancel. The other two add up to 1. So 5 halves times 1 is going to be 5 halves. And so that's our first triple integral, and it equals 5 halves. So this is a nice rectangular domain. I'm going to do one more example that also has a rectangular domain. Okay, it's gives you a little sense of how we can use triple integrals in some sort of application. This says that a cube C has sides of length 4 and is made of a material with a variable density. That density, I believe on your handouts, that density is going to be a rho. So the density is rho of x, y, z, and it's equal to 1 plus x times y times z, grams per centimeters cubed. And we want to find the mass of the cube. So here, just like we did with these two-dimensional metal plates, we integrated the density of the plate in 2 dimensions. That gave us the mass of the plate. Now we've got a density given in 3 dimensions, grams per centimeters cubed. We're going to integrate that density to find the mass of the cube. So this is a metal, this cube has a side length of 4. So we're going to integrate from 0 to 4 in each dimension. And we want to integrate the function, which is the density, 1 plus x, y, z. And we want to integrate that dx, dy, dz, for example. We can put those in any order we want. And so I want to do that integral to find the mass, but I want to be smart about how I do this integral. And so what I'm going to do is I'm going to integrate from 0 to 4 in each direction. And I'm going to write this as the triple integral of 1 dx, dy, dz plus the triple integral of x, y, z dx, dy, dz. And the reason I'm going to do that is that when you look at the first integral, I'm integrating 1. So I'm integrating like a density of 1 from 0 to 4 in each direction. And so that's just going to give me the volume of the cube. So this here, this is essentially just the volume of the cube. And so the volume of the cube is 4 cubed. And then I can split up the second integral quite nicely. It's the integral from 0 to 4 of x dx times the integral from 0 to 4 of y dy times the integral from 0 to 4 of z dz. And I can do that because this is a function of x times a function of y times a function of z, and I can consider those integrals separately because x is constant with respect to y and z, y is constant with respect to x and z is constant with respect to x and y. Okay, so this actually makes the integral quite easy. So it's 4 cubed plus, okay, I want to integrate x dx from 0 to 4, so I will get 1/2 x squared evaluated between 0 and 4 times 1/2 y squared evaluated between 0 and 4, and then times 1/2 z squared evaluated between 0 and 4. And so I'm going to get 4 cubed plus, let's see, 1/2 x squared, so that's half of 16, or 8. So the first integral, when I evaluate it, is 8. Of course, the other two are also going to be the same, so that's going to give me 8 cubed. So I get 4 cubed plus 8 cubed. That gives me 576, and then that's supposed to represent the mass, so that's going to be 576 grams.